So good evening students. So this is live interactive session week 8 for the course of traffic engineering. I am Suman Ganguly. I am a PMRF research scholar at IIT Kharagpur and the course instructor is Dr. Bhargav Murthy. So this is about car following theory which actually comes in your module, I think week 9 module F. So first we will go through the topics that have been covered, but before that, if you have any queries, you can raise your hand and you can ask. And for this session, first I will go through these topics that have been covered, and then I have some MCQ, mostly MCQ questions, 3, 4, 5, 6, 7, and then also which is not included in the PPT. I have one numerical that I will be explaining here. I will not be solving here because it's in a tabular form, so it will be difficult for me to solve here using this PPT format. So I will just explain that problem and then I will finish this session. So let's start. If you do not have any question at this beginning, so maybe I can start. So this car following model is started with the concept of space headway and time headway, which we already talked about in the second week 2. So basically space headway means if you consider like this, so suppose you have two vehicles or any vehicles. So if you see the center to center gap between this vehicle in terms of distance at any instance, it is called the space headway, right? So space headway is directly related to the density of vehicles, right? The density of a traffic stream. So what is density? Density means number of vehicles that can be crossed at a particular point at a particular time period per kilometer. That is the density. So now if I have a 1 kilometer road, that is 1,000 meters of road if I convert it to meters, and if I have space headway, suppose this is H or HS, so this will be equal to what? This will be equal to K, right? So if the spacing between if the distance space headway or the distance between two consecutive vehicles are HS in a traffic stream, so then in 1,000 meters, so there will be how many vehicles? That is called the density. So then we come to the car following models. So there are many car following models, and even nowadays also scientists are developing different car following models to suit their field conditions, right? So if we like one of the initial car following models was the Pipes theory and Forbes theory, right? So but basically these models were developed in the Western countries like US and Europe. So it may not be directly applicable to our Indian context, right? Also, I do not also think that we have explicitly developed any car following model for countries like India. So there is a scope of research uh, for this to develop some car following models. But let's we understand that what do you mean by car following model and what is the necessity of this car following model. So basically, in a traffic stream, so one vehicle obviously will follows the other vehicle, right? So if it's a lead vehicle, it will be a follower vehicle. So this is how our traffic stream interacts, right? Or vehicles will interact in the or on the road or in the traffic stream. So now obviously your response of your following vehicle will be depending on this lead vehicle. So if your space headways are large, so there will be kind of no interaction and vehicles can move in a desired manner or with a desired speed, right? Desired speed means in a free flow speed, like whatever the free flow speed or posted speed limit is there on that particular stretch, I can achieve that speed freely, because I do not have because maybe for 500, suppose there is a long space headway. So suppose, let's say 5 meter is your space headway. So now because you have a long space headway, so they are not directly interacting, right? So then if it becomes closer, your space headway becomes small, then obviously if this reaction of this vehicle will depend on the reaction of this vehicle. If that is slowed down, I have to be slowed down as a follower, because if I am not slowing down my vehicle, so there will be collision or there will be accidents. So this is about only longitudinal communication or longitudinal interaction. So also, whenever any vehicle want to change their lanes from, suppose there are two lanes, so this is one lane and this is other lane. So now you want to overtake and change the lanes. Here also there are some vehicles, right? Suppose if it's a one-way road only, not two-way. A two-way also, for that also it is true. So now if it is a one-way road, so now it's a faster moving vehicle, now you want to change the lane. That's where also you are also following the vehicle, right? So it's a lane changing model, right? Not a longitudinal interaction. So there also the interaction will be there. So if there are too many vehicles on that stretch, so your this vehicle will not be able to enter here and cross it, right? So so also so these are the major things. Also there are many other things. So basically that's why we need to develop the car following model, because it is the way, that's how your vehicles are interacting. So then some pipes theory and force theory has developed. So I may not be going into the details of pipes theory and force theory, because the more important and more famous theory is General Motors car following theory. So I will be explaining the General Motors one, but if you have any difficulty, maybe in the later stages, maybe I will I can explain those pipes theory and force theory. But I think it is simple enough to understand. But one thing we can mention, that because there are several limitations of this pipe theory and force theory, basically General Motor has come up with some new kind of car following models. So now if I just remove this, we can start with the General Motors car following models. So first is the first generation General. So basically, before I just say, I can say that it is like that, because I already told you that car following is about the interaction, right? So what is the response of the following vehicle? So you can generally, you can say that response, response is a function of stimuli, it is already given in the PPT, and the sensitivity, right? So this is your model, the car following theory and the concept. So response means in terms of whether I should accelerate, whether I should decelerate my vehicle, or whether I should remain at the constant speed, right? So that is called the response, right? Acceleration, deceleration, or no change at the same speed. So then your stimuli means your that response will directly depend on the relative velocity of the leader and the follower. So relative velocity between lead and follower, that is called the stimuli. So based on that, I will change my acceleration deceleration strategies. So there is something called sensitivity, which also influence my acceleration deceleration. So but how it is different from stimuli? Stimuli is a thing that is like that's a necessary thing to consider here, because obviously if I am traveling at the same lane at the same direction, so based on my relative speed, I should be able to adjust my vehicle, or I should maneuver my vehicle in order to properly react, whether it is acceleration or deceleration or something else. So now in case of sensitivity, so your sensitivity actually influences the magnitude of acceleration and deceleration. Because suppose uh, two vehicles like this traveling on the same direction, one is a velocity is 150, suppose, let's say. In other case, maybe hypothetically 150, or maybe 200 and 150. In both the scenario, if you see, the relative velocity is 100 minus 50 is 50, because it is going in the same direction, and here also it is 50. But see, the both scenarios are different, because the speeds or traffic stream speeds are higher in this scenario, so there is a more chances of having collision than the previous scenario. So not only relative velocity obviously it is important, but with the relative velocity there could be some other factors that is also equally important, and those actually uh, integrated in this sensitivity factor. So what are those two factors? So here sensitivity generally in case of General Motors or GM's carpooling model, these are two factors. First is your space schedule. So what is the distance between two vehicles, existing distance? So if they are too far apart, so your chances of collision or probability of collision will be less, not more. Like, and your sensitivity also will be less. And in case, and other thing is your speed of this vehicle. So even if I told you that, even if your this vehicle speed is 100 and this is 200, and even if your both relative velocities are same 50, so here because the speeds are higher in case of 200, so there is a greater chance that you have to adjust your speed. The follower have to adjust your speed quickly, or the magnitude of reaction will be quicker or higher, we can say. So based on this, these sensitivity factors are developed. So now we can actually go to the first generation and other models. Now in case of first generation model, the thing is, the assumption is that your acceleration of the n plus 1th vehicle or the following vehicle, right? N plus 1 is the following vehicle. So if I say x dot dot, that will be acceleration. So your t time at any instance t, and if your del t is your response time, right? So that actually equal to alpha cross your directly your relative velocity, which is the stimuli factor, right? That is the basic necessary factor that you have to account. So x n plus 1 t minus x dot, which dot represent velocity, x dot, and x double dot represent the acceleration, right? So for nth vehicle at time t, this is the your acceleration, right? So now this factor is the sensitivity factor alpha. So we know that your response, this is response, is depending on your sensitivity as well as your stimuli, right? So this has been kept at constant for first generation model. This is called GM's first generation model. So there was a disadvantage of using this model. So people have found out using several experience. So as your t gets higher, your alpha's values also gets higher and ranges from I exactly don't remember, but it is a range of like maybe 0.12 to 1.74 or something. So it's a large range. So now we understood that it depends on the t. So at time, how del t changes, how your reaction time changes, not t but del t. So for like your alpha sensitivity depending on your time, so it is not a constant at all times. So based on these field observations, people realize that we need to change the, or we should not use this kind of constant alpha value for a particular scenario, since it's largely varying. So now people come up with the second order or second generation GM scaffolding model, where they have included either alpha 1 or alpha 2, like that. So whenever your space headway is larger, so lower sensitivity value has been preferred. Whenever your space headway is lower, in that case of higher sensitivity value has been proposed. So why is that? Because if your space headway is lower, that means your vehicles are closer, so there is a more chance of collision, right, or interaction at least. So your sensitivity is higher because your magnitude will be higher, and alpha will, because it's alpha into some factor, so it will increase your acceleration. So that means you will quickly react. So okay, so now, and vice versa, right? So now in case of third generation model, what people have realized that actually how to define that low headway and a low space headway and high space headway. Now what we told, that if your space headway is large, then you do this, if your space headway is small, you do this. But how to even know, or how to even determine that what is that low and what is that high, because there is no way to quantify it, right? So now people have realized that we have to use that space headway factor into account. So because it's a inverse relationship, as your space headway gets lower, your sensitivity gets higher. So now they have proposed the third generation model, where they have used this alpha equal to alpha 0 by this headway means xn plus 1 at time t. This is the follower vehicle, right, and this is n is the leader vehicle. So this is they have proposed into the same factor, right, the relative velocity. So that is the third generation model. So why it is so important? Because it is already you have accounted for this space headway. So depending on your value of the space headway, it calculates this, and it uses a constant alpha 0 value also for, because now how they have developed it is that they saw that what is the your alpha value, how it is changes based on the space headway, and what is the remaining value you need to adjust for this your actual alpha value. So they have actually multiply or divide or multiply a alpha value so that it can be adjusted your actual values. So that is called the constant factor, right? So it's a dimensionless quantity, it's a constant. So this is the third generation model. So now in case of fourth generation model, because they are constantly improving it, so now in case of fourth generation model and fifth generation model, they have two models. So what they did in case of fourth generation model, they also hypothesized that it is your acceleration or reaction is obviously depending on your relative speed as well as the space headway. But even if you consider, or if you imagine two scenarios where both scenarios are same, but your speed of this vehicle is more. Suppose let's take an example where your suppose relative speeds are same in both scenarios, right? Suppose it is 60 and it is 30, so your relative speed are same, and your space headway values, suppose it should be center to center, but maybe it is suppose let's say hypothetically 20 meters. Now the same scenario, but only the difference is your this is 70 or maybe this is 40, like that, something like that. So now if you imagine this, because the speed of this traffic stream or speed of the following vehicle is high, so there will be like his reaction will be more quicker, and the same, if we imagine the same traffic roadway condition is prevailing at both the both the suppose there are two different roads, and both the roads the traffic and roadway geometric conditions are same. So for that, to take into account, they have included this of n plus 1, which is the follower vehicle, right? So this has been included in the fourth model. So in case of fifth or the last or the updated this, or we can say the generalized form of this car following model, which actually we are nowadays are using. So that expression is similar, but they have generalized it. So how they have generalized it? So they have included alpha L comma m, and in the speed they have included this m factor in terms of speed headway to the power L, and then into the relative velocity. So it is the generalized model. And why they have come up with this m and L factor? Because they actually found out a beautiful relationship that exists between this car following models and the macroscopic traffic models, especially the Greenberg's model. So they have found that from this we can actually we can come to any of the macroscopic models. So from microscopic model we will be able to come up, or we able to derive our macroscopic models. So based on different m and L values, you can get different Greenberg, Greenshields, right? This is logarithmic actually, and the exponential model and other two regime models. So as soon as they found out the relationship, and it is an interesting discovery, since it's a one traffic stream only, but we are analyzing the traffic stream in both ways. One is microscopically, that is the vehicle to vehicle interaction, how those are things are interactive in longitudinally, in laterally, right? And also aggregated in a aggregated way, speed density relationship, how that fundamental relationship, how we are actually correlating it. So this is a discovery, and this is one of the reasons why it is still a famous model, this General Motors model, because it beautifully describes the relationship between a microscopic traffic parameters and macroscopic traffic parameters. Although at what extent we can use this kind of models in Indian context, that remains a question, and that we cannot answer right now, because Indian traffic is something different, because we not only having the cars or motorized vehicles, even we have the non-motorized vehicles as well in the traffic stream, like our cycle rickshaws, our cycles, even sometimes in urban areas. Also we have different kinds of different sizes of vehicles, not only cars but also trucks, vehicles, small trucks kinds of things, and then many other things, even recently the e-rickshaws. So the interaction is even quite unique. As for example, suppose you will be always be seen in Indian context. Suppose there are this kind of vehicles. So actually, if this narrow is, suppose it's a motorcycle, two wheelers, right? So generally it comes and sips between the two vehicles. As soon as I find the gap, I will sip and I will come to this. So this kind of shipping behavior and also is actually unique to the Indian context. And also um, suppose there are suppose three lanes, right? 1, 2 and 3 lanes. So if you carefully see, if there are like this 1, 2, 3 lanes, so always in closer to the signal you can see that suppose 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 this is one bus, this is the car, and this is vehicles. So here also you will see the autos are waiting, here also you see these motorcycles are waiting, and like that. So you will see the not only three vehicles, maybe four, five, or even six vehicles sometimes are actually accommodating in a three-lane road only. So this is also quite unique in case of India. So this that's why this car following models, like even the longitudinal interaction, the lateral interaction remains a challenge, and actually even some IITs also, they are actually conducting this kind of studies, that how to actually model this kind of Indian car following or general vehicle following behaviors, right? So that's an interesting area to explore actually. So okay, I won't be saying that what M and N value leads to what model. Maybe later on, whenever we will discuss the quick Q&A session, that time we will go through these things by opening the actual PPT maybe, because I even don't remember exactly the M and N values. So now there is a concept called traffic stability. So suppose in a traffic stream, some vehicles, some leading vehicles are there and some following vehicles are there. Suppose due to some influence of alcohol or something, uh, because generally due to alcohol your consciousness actually reduces, human consciousness. So maybe even if it slows down, I am not slowing down as a follower vehicle, and then suddenly I applied the brakes and the accelerations very quickly, right? So that's a abrupt reaction, right? It may not be necessary, but due to maybe some influence, even some drivers, even with the absence of alcohol, they are aggressive, they remain aggressive, so they can do this kind of behavior, they can show. So this kind of higher or we can say that higher abrupt behavior or higher tendency of acceleration with the lower or the delayed reaction, this actually leads to unstable behavior. Whereas if you stable behavior indicates that if I saw the vehicle is slowing down and I am also slowing down, so it will be a kind of uniform or slowed reaction, not a abrupt reaction that is causing any problem. Because in case of unstable behavior, it might lead to some kind of problems in the road, right? Because the sudden due to the sudden braking, maybe my vehicle skids or something like that may happen also. So this is called the stability and instability of the traffic. So there is something also called the local stability and asymptotic stability. So what I was discussing about, only considering only two vehicles, and how suppose there are only two vehicles and one vehicle in the leader vehicle abruptly changes its speed, so it might affect my follower vehicle if the obviously if my space and time midway is small, right? So but it may not impact the overall traffic stream. Suppose you have a chain of vehicles like that, 1 2 3 4, suppose it's a two-way one-way two-lane traffic stream like that. These are the vehicles. So maybe this impact this, but it may not immediately impact this. So it's a local disturbance or local stability that has been compromised, not the asymptotic stability. So what do you mean by asymptotic stability? Whenever you are impacting this traffic in a serial order, like if your vehicles are is less spaced, and also travel times are relatively high, or travel speeds are relative, not travel time is high, travel speeds are relatively high. In such case, if your one vehicle is creating some kind of nuisance in the lead role or as a lead vehicle, then it can impact actually a longer chain of vehicles, right? So I remember one video during COVID. I think in the Jamuna Expressway, they are actually due to fog. Actually, people are unable to see the road. So there was one vehicle which was breakdown due to some problem, what I remember, and vehicles are coming very fast because it's a expressway, and they are actually colliding with the vehicles, and it's a chain event. I actually saw in the TV that at least I saw some 5, 6 or 7 vehicles, they are actually colliding within a fraction of seconds. So you can imagine this kind of asymptotic instability may occur due to different reasons. So now there is another car following model which is called a Wiedemann car following model. This is developed in Europe, unlike GM's car following model, which was actually originated from US or America. So in case of Wiedemann car following model, uh, it model 4 conditions. So it models free driving, approaching, following, and braking, right? So suppose you are driving in the early morning in a road, even if it's an urban road, so you see relatively less number of vehicles are traveling, right? So they are actually, you can imagine, you can do a free riding, right? Because there are space headways are very large, so there is no issues or no point that you have to react or you have to change your acceleration or deceleration. You can free flow, you can move at free flow speed. So that is called the free driving. Now whenever you are approaching a certain vehicle, so that obviously you have to react, but the reaction will be lesser, not higher, because you are approaching, you have, it is not that you have approached or it did some kind of abrupt reaction. So you are approaching, so your behavior will change. So it has also modeled that approaching behavior also. And then it's following, it's a following state. Suppose during morning peak hour, not like obviously it's a peak hour, but uh, suppose the capacity or the flows are not that much of hampered till now. Already peak hour started, but we are able to move freely or not freely. We are able to move on a consistent basis without stopping or without stucking at traffic, right? In those scenarios, your vehicles, your consecutive vehicle pairs are following just leading vehicles. So that state is the following state. And then you are braking. Suppose there is a signal, you have to brake. One vehicle is slowed down or one vehicle has stopped, and all the vehicles has to be stopped. And it also some other kind of scenarios you can think of in terms of braking, right, to avoid the accidents. So generally, if you imagine, these are the 4 scenarios which even in the reality these scenarios are actually occurring, right? Now you can say that okay, your GM's car following model also developed, so it can also, in terms of free driving, it will be also able to detect and model your car following. So why you need Wiedemann car following model, for what purpose, right? It someone may have developed for European purpose, but how those topics are different, because those are lane discipline traffic, unlike India, which is a not, they are not actually lane based traffic. These are non-lane based traffic. So in that case, the thing is, in case of Wiedemann car following model, so so small disturbance, actually generally as a driver, human drivers, we don't really react until it's a severe scenario, right? In terms of smaller variations, we generally don't that much react. So those kinds of fine tuning of these models has been incorporated in the Wiedemann car following model, unlike our 5th generation or final generation GM's model, right? So that is one of the advantages of the car following model. And also there are some advanced traffic simulation software. If you are familiar with any traffic simulation software, so there are many traffic simulation software, uh, Linsync, Sidra, then Visim, then CoreSim, then Sim Mobility, then so there are plenty, right? So in some famous softwares like Visim, which is actually developed in Germany, and it is developed by Karlsruhe Institute of Technology, I think. So actually, so they have used this Weiderman car following model, and they have actually made this model famous. So there are two versions of it. One is the 1974 and another is the 1999. So 1974 actually it was built for urban traffic scenarios. So also if you imagine your urban traffic scenarios and your rural traffic scenarios, or your national highways, the traffic operation, and your normal urban streets, so those are quite different. So you have to model it in a different manner, because your urban scenario is more complex than your rural scenario, right? So now, so that's why your initially 1974 model was developed for the urban traffic, and your 1999 model is developed for the rural traffic or the expressways, right? But later on, due to the higher flexibility of your car following model that has been developed in 1999, people or researchers actually used this 1999 model also for urban scenarios, because it has some more parameters to model it, right? So then we come to this simulation, and what is the need of this simulation, right? So there is something called a system. So if you imagine everything is a system, so your traffic stream is a system consisting of vehicles, consisting of drivers, consisting of roadways, consisting of traffic control devices like traffic signals, your uh, markings, like they are interacting in unique ways, right? So that's called a traffic stream, and traffic stream, you can imagine it's a system. So anything in reality, it's a system, right? So now your traffic stream is a system, and it's actual system, obviously. So it's not a model, it's a system. But suppose you want to experiment, or you want to know that how your different parameters are affecting, suppose your traffic flow. So traffic flow is a macroscopic parameter. Now you want to develop a relationship between a traffic flow and other traffic characteristics, right, for a particular scenario. So how you want to approach this, because it's actual system. So you can say that I will collect traffic flow data, I will collect traffic speed data, and I will collect traffic density data, or some other data, whatever you need. Maybe driver response data, in terms of if you want to model the driver responses, and then I will make some models, right? Then based on that model result, I want to give you that, okay, this is the result. That is the traditional way how the macroscopic models are even developed. But traffic, if you see, it's a much more complex system than only developing a speed flow density relationship. So if you develop a speed flow density relationship, but still you have not developed that how your time headways, your space headways, your other parameters, how those are impacting your flow. So it's a complex thing, right? So people have tried to do it using the field data, but one of the good option is to use the simulation. So now in terms of classification, so this is a system, right? Now for experimenting such things, generally what we use traditionally, it's called a model. And another thing is prototype also, right? So you can imagine it's a model or it's a prototype. So prototype means you are building something. So in case of traffic, so if you want to build a prototype, that is a physical model, so it is very difficult. So how do you want to model it? So are you going to buy cars and motorcycles and build a traffic, and that you cannot replicate anything, because that doesn't make sense, and that kind of huge system you cannot develop. So generally in case of model, we generally reduce down, or we scale down the model, and we build a prototype, right, for replicating it. But in case of traffic, it may not be possible, because it's a challenging thing, right? How do you want to develop a physical model? It's virtually it's impossible.
So now the second is mathematical model. Obviously, we already developed our microscopic and microscopic models. So there is a scope that you develop a mathematical relationship. So now your mathematical relationship, so you may develop any model, but it is not necessary that your model is having a solution. So uh, we we already know that there are some mathematical model where trivial solutions are possible, and in some other scenarios where trivial solution are not at all feasible. So in case of infeasible solution, what should we do? So that's a question mark, right? So if we have some complex mathematical model, and if we know the answers, right? So if we know that okay, it can be solved maybe in a simplistic manner, considering some assumptions. So because without assumptions you cannot solve it. So if you read any mathematical model related to traffic engineering, this kind of traffic flow model, this kind of simulation model, right? So you will find that there are multiple assumptions are there, because you want to reduce the complexity, you want to have a simple solution, right? You want to reduce that complex problem into a simple entity, and then you want to get a solution, at least a representative solution, closer which is closest to reality. So then in some other cases it may not be possible, so because it's a such complex process. See, so in those complex scenarios, so there is something called a simulation model. So simulation model, basically they are using the advancement of computation, right? Computers, computation, digitization, they are using these advantages, and they are actually replicating your traffic stream scenarios, and also the relationships. They have some kind of models. They also, in the traffic simulation, there are mathematical models that are involved, but you do not have to see those mathematical models, because it is already developed by someone. So now they are giving a computerized model. You just learn to use that model, and you use it for your purpose, because every time if you have to build a mathematical relationship for each scenarios, so it's a very challenging thing, and it is not a feasible thing. And also, I already told that in terms of mathematics it is not possible to include everything, but in simulation, at least if we can calibrate it properly, so we will come to that point, that what is calibration. So then actually we can use it effectively for different purposes, right? Even traffic engineers nowadays, they are very fond of using this traffic simulation models. So now already I hope that already it is discussed now, at least in queuing, that something there is called deterministic queuing, something there is called stochastic queuing, right? So stochasticity means that during different time periods of the day, your traffic flows, microscopic parameters like speed of individual vehicles, time headway, space headway, those are constantly changing. Those are not a fixed quantity. It is not like that previous time period the traffic is 20 vehicles per hour, in the next time period, say after 1 hour also it is 20. It is highly unlikely. So it will vary, right? It will vary within the day, it will vary during different days of the week, right? So even during season, like in the winter season, traffic flows are high generally, and in terms of in case of summer season, the traffic flows are low relatively. So there is something called the deterministic and stochastic, and generally our traffic process is stochastic. So this makes even your mathematical model much more complex, because it's now a stochastic process. So the values are evolving with time, so it is very challenging to do it using any kind of even analytical model. Sometimes that is a simplistic version of a mathematical model. So now we comes to the traffic micro simulation model. So already I described to some models like VCM and all. So those are traffic simulation models, or I can say the packages which is available. It's a form of softwares that you can learn and you can use it. if your basics are clear regarding the traffic processes. So this micro simulation means, micro means it is using microscopic parameters, so it has an advantage that it can model your vehicle to vehicle interaction and give you results, right? Because sometimes without considering your, so suppose you want to, suppose let's take an example of any microscopic parameter. Suppose you, like I already talked about in the second module, I believe, that time headway distributions, that intermediate headway distributions, random headway distributions, right? So where we saw the Pearson type 3 distributions, normal distribution, then the negative binomial distributions, right? So that's a time headway distribution. So what is the time elapsed between the two consecutive vehicles on a traffic stream? So such distributions, suppose you want to know that what distribution it follows along a urban corridor, along a urban stretch. So then for that if you are using macroscopic parameter which only have three parameters, speed, flow and density of a traffic stream, we do not know the individual vehicles, so we do not know the interaction, so we do not know the time headways. So it is not possible at all to actually calculate those things without using the traffic micro simulation models, right? So that one of the examples I gave you, that at what purpose or in which occasions you want to use this traffic micro simulation models. So now, so there are some steps before you are using a traffic micro simulation model. So suppose as a part of input, so suppose so input is okay. So there are in any transportation related project, so there are two types of inputs. One is supply, another is demand. So what is supply? Supply means what is the number of roads, how much, what is the number of lanes, what is the width of the lanes, is there a signal placed at a intersection, what is the intersection geometry, is there a roundabout, what is that geometry of the roundabout. So these are supply kind of factors. So people build road to, so that I can use that road, right? So now what is the volume or what is the demand of vehicles, what is the volume of vehicles that are coming to that particular road, which are called the demand related factors. This is demand, traffic demand, right? So now also suppose you have developed a road for certain speed limits, so you have to mention the speed limits in the simulation model, right? So first thing is to develop the network. So once you develop a network, suppose it's a road, you want to develop one road with 4 lane divided, so 2 lane either ways, and 3.5, whether there is a footpath or not, you have to develop, right? We have to create in the model itself. Then whether parking facilities are there, you have to create. So all the things, all the elements you have created. So now you want to give the vehicle inputs or the demand inputs. So how many vehicles are going to which direction? Because if there is intersection, so some vehicles will go right, some vehicles will go left, like that, right? So that is called the demand. So once you have supply as well as demand, and also in terms of supply, the signal cycle length, what is the green time at that particular signal. So these will be, this we have to collect in the field. We go to the field, we collect volume data, we collect the signal cycle data, we collect the number of lanes, or you measure the width of the lanes, right? And also what is the free flow speed in the morning based on the speed limit, what is the typical acceleration, right? So you want to know that what is the typical acceleration or maximum acceleration, because otherwise it's a computer program. So maybe it is developed for some countries, so they have their default values. So now you have to replicate your field scenario, not their field scenario. So also in case of Indian context, you want to include the cycles, you want to model not only the cars but also the buses, but also the cycles, trucks, different vehicles. So you can model it, there is a flexibility is there. So once you model it, demand and as well as the supply factors. Now you have to calibrate it. So what do you mean by calibration? So suppose you have given input of 1000 vehicles. So now you are saying that you are seeing that after running for 1 hour, which usually in the field in 1 hour 5000 vehicles are crossing. So you have given input to 5000 vehicles, but now you are seeing that no, only 4000 vehicles are passing along that simulation model. So now there is a deficiency of 1000 vehicles. So 1000 vehicles means your if you calculate the errors are very high, right? So then it is not replicating your field scenario, because now you are unable to actually replicate the field scenario. So your vehicle, at least your 5000 vehicles or closer to 5000 vehicles in a 1 hour should pass, but it is not passing. So now you have to adjust your car following parameters. Now the car following parameters comes. So car following means how your vehicles are interacting, right? So is it following the lanes or not? If it is not following the lanes, what is the behavior? So is it that the the queuing is diamond shape or queuing is normal as we observe in the Western countries or the developed countries? So there are many factors that you have to change or you have to calibrate. Now you can say that there could be many factors which how can we measure the values. So suppose what is the reaction time, how can we measure the values? So okay, that's a real problem. So everything can be measured because it's a microscopic thing, you cannot measure everything. So for that actually you have to calibrate. So you have to tune up your parameter in such a way that your field observed MOE means measure of effectiveness. Measure of effectiveness means suppose your flow, your 5000 flow should pass. So your flow is measure of effectiveness. Suppose you have taken the flow as your measure of effectiveness for that particular model. So now your 5000 and your 5000. This is real field and this is simulation. That should be 0 or at least that should be minimized up to a certain threshold. Maybe suppose we can say that okay, 5%, if it is varies within 5%, we can reasonably accurately representing or calibrating our replicating our field scenario. So for your that original minus field flow to be minimized, what are the parameters or what is the value of this parameter? Suppose those parameters may range from 0 to 50, 0 to 60. So what is that particular number? What is the optimum number? So it's a optimization problem, right? It's a minimization and most particularly it's a optimization problem. So if you solve this optimization problem, you will get the parameter values. So now with these parameter values you can do whatever you want. So suppose you are saying that that using a particular signal related parameters or signal configurations, you are observing a higher delay. So now you want to modify your signal parameters, means you want to modify your green time, you want to modify your red time or red interval. So now how can you do it? So once you have a model, you change your green values, red values, different combinations, try it and see that what is it impacting your flow, how it is impacting your flow, right? So that's how you can use a simulation model effectively to replicate any field condition. And also stochasticity, because there could be stochasticity in the field. So if you go and measure, suppose the time is 10 to 11 in the morning and you measure that traffic flow is 4000 at a particular stretch. If you go during some other day, we may find that it is not 4000, it is 4200, maybe sometimes it is 3800. So this kind of fluctuations are there. That's why in traffic simulation also we have something called random seeds. So random seed means it will randomly change your value in a closer range, right? So to replicate that field conditions, and whatever you find, you can take a average value to represent your actual field conditions, right? So that's what in a nutshell the theory. So if you have any queries till now, you can ask. Meanwhile, I will just drink some water, then we will go to the Q&A session.
So in case of Q&A session, I will encourage that I won't be saying the answers initially. Maybe in the beginning you can try it, and maybe in the chat box if you want you can say that ABCD whatever, whether it's wrong or it's right, that doesn't matter, but at least if you can do it, you can follow this, and then I will be maybe explaining. These are simple questions. There I don't not think that there is a need for much explanations, but still I will be explaining something. So should I go to the next slide or should I wait? If you have any queries you think of, you can ask, or if not, then I will move forward. So shall I move forward then? I take it as yes. So maybe you first try. I already actually discussed that what is called a stable traffic behavior of vehicles and what is called the unstable traffic behavior. So the question is how you have to match the driving behavior given in column X with the corresponding reaction times and sensitivity parameters, right? So there are only two things. Other one is high reaction time, then the low reaction time, and then the high sensitivity and the low sensitivity. So what is representing which of these options are representing the stable traffic behavior and which of these are representing the unstable traffic behavior. So shall I expect to get an answer from you or no? So maybe I will be waiting for a couple of seconds. You can think. If you can just in the chat box you can write the answer whatever you feel, that one is this and that and two is this and that. So if you imagine or if you remember previously this is what I was explaining, that you are not reacting even if your lead vehicle has abruptly changed or at least it changes its course. You are not reacting as a follower vehicle, then suddenly you are reacting. So that is called the unstability behavior, right? This is called the instability in the traffic stream. So instability means you have high reaction time or low reaction time. So you are not reacting means your reaction time is high. So you are taking more time to react. It should have been that you should be reacting in a quick manner so that you do not have to accelerate or decelerate more. But because you are not doing it, so you are delaying your higher reaction time. So your 2 obviously it is A, and obviously your 1 is your B. And then because your reaction time is high, your sensitivity is also higher, means your reaction time is your acceleration will be quick, so your sensitivity will be quick. Okay? So this is what 2AC and this is what ABT. So any queries up to this? If you think other way around, you can ask or you can discuss. No? So this should be the answer, right? So this one is the accept and reject type question. Question 2. So your lane change behavior of a model can be modeled in a micro simulation model. Okay, just 5 minutes ago I was discussing this. So is it accept or reject? Tell me. So your car following model, I told you that it not only accounts for your longitudinal behavior but also accounts for your lane change behavior, right? So is it that your lane change behavior can be modeled in a micro simulation model?
Do you want to respond to this? So basically in car following model it is included, and obviously because car following model is a microscopic model and micro simulation, obviously it's necessary that it includes the car following models. So obviously your car following behavior can be modeled in a micro simulation. So it is an accept, not a reject statement. I think it is clear to you. So then the third one. So General Motors third car following model is a simplified model which can be obtained from generalized GM car following model by taking values of distance headway exponent as. So distance headway means this m exponent is what? Wherever you are given the speed exponent is 0. It's a simplified model which can be obtained from generalized car following model. So you can try to answer it. Maybe I will go to this week 9 module once, so that I can also brief you about so if I can show you that graph, it will be more clear that at what value what is happening. See, your distance headway component is L, your speed component is M, right? So M and L. So now your third generation, in case of third generation model, your M will be 0 and your L will be 1. So here your M is what? M is your, okay, there is a confusion. Your M is what? Your M is the speed component which is 0, and your distance headway component, it is actually L. So your L equal to 1 and M equal to 0. So this is actually from generalized car following model you are getting the General Motors third car following model, which is basically accounts for this alpha 0 and the distance or space headway and then the relative velocity. It does not include your speed component, which actually introduced in the fourth model and fifth model. So this is what your the answer is. So L equal to 1, M equal to 0. So even if you remember only the generalized car following model, which is x acceleration n plus 1 t plus del t equal to alpha L comma m into speed of the following vehicle at t plus del t into this will be m and your distance headway x n minus n plus 1 t minus x minus 1 t to the power n. So now so suppose now if you place your m equal to 0 and L equal to 1, into obviously relative velocity. So now you can obtain this relative velocity. This is n equal to 1 and this is to the power 0 means 1, right? This to the power 0 into alpha. Right? So this is nothing but your third generation model. So now similarly any values in any valid values you can actually go back to your that fourth generation, because the fifth generation is the generalized model. So you can obtain your fourth generation model if you change your L and M value. So if you remember this model, it is sufficient for you to calculate the other version of the models. So then which of the following statements are true with respect to pipes theory? So pipes theory is based on the distance or safe distance between the two vehicles. It is depending on the speed by your that values. So now as speed decreases, the minimum safe distance increases, because it directly have a proportional relation with the speed. So as speed increases, your safe distance value will increase, not decrease, because once your speeds are increasing in a traffic stream, so vehicle has to be careful because your speeds are high. So now you will maintaining more safer headway distance, not less. So that's why it is not true. As speed decreases, your minimum safe entry should decrease, not increase, right? So it is not true. So as speed decreases, your minimum safe time headway decreases. So if your speed decreased, so obviously your safe time headway, not distance headway, time headway will increase, because you are running at a lower speed, not at a higher speed. In case of higher speed, your distance headway will increase and your time headway will decrease, right? But it is opposite for decreasing speed. If your speeds are decreasing, so vehicle will come closer in terms of space, but in terms of time it will be more spaced in terms of time headway, because you are going slow, so your time headway will be increased. So it is also not true. So then possible flow rate increases with increased speed until traffic capacity is reached. So it is saying that possible flow rate increases. So if you increase the speed of a traffic stream, then your obviously flow rate increases, because you are increasing the speed. So more and more vehicles will flow through a particular location. What is flow? Flow means what is the number of vehicles those are passing through this point at a particular time, right? So now, because you have increased the speed of the vehicles, speeds you have increased, so your flow rate, that will increase obviously, right? But once you reach the traffic capacity, if you increase too much the speed, so their space headways will be so much higher, so your that flow rate will obviously decrease. So this is, if you imagine this kind of curve, right? So this was the curve. So once you reach the capacity, it will decrease. It's a standard curve, and it is just saying the same thing, your pipes theory. So at lower speed, all vehicles in a car following model maintain near minimum headways. At lower speeds, so whenever your speed is lower, okay, so all vehicles in a car following mode maintain near minimum headways. Minimum safe headways they will only maintain at lower speed, because their speeds are lower, so they do not have to increase their headways. Here headways mean obviously space headways, not time. This has to be remember, this is space headway. Generally headways means space headway until we mention that it's a time headway. So obviously because your speeds are less, so there is no fear among the drivers that they will collide, right? So they will come packed or closer to closer, so they will only maintain the minimum safe headways. So these are the two correct options. So is it understood, or do I have to repeat some part of it? So is it understood? I think it is understood then. No? Okay. You have anything to ask? Hello? Yes, you have anything to ask? Okay. Okay. So the type of performance measures are given, not is, but are. The type of performance measures are given in column X and the corresponding performance measures are given in column Y. So you have to match the column X with the column Y. So in column X it is written the point measures, link based measures and the corridor bus system measures. So here measures mean the performance measures, right? So also the speeds are given: average vehicle speed, space mean speed, spot speed. So that means you have to imagine, suppose you are evaluating uh, a traffic corridor and it is considered as a system, right? So now what kind of performance measure is you should take? What kind of performance measure? So it's a corridor. So suppose it's a like that, it's a corridor consisting of maybe one signal, two signal, then maybe three signals, then maybe this is unsignalized intersection, and these are maybe signal 1, signal 2 and signal 3. So now your traffic is moving in this direction, right? So it's a, you can say that it's a corridor. It's a, maybe the length of the corridor is maybe 10 kilometers or so. So what kind of performance measure should I choose? So is it a spot speed? So generally what is a spot speed? We generally have something called radar guns, right? So if we have the radar guns, so if it's a traffic stream, we generally point the radar gun towards the vehicles and we measure the speeds. Spot speed. Spot means at that particular location what are the speeds of these vehicles, right? So it is called the spot speed. So there are, if you remember that time mean speed, how you calculate. Suppose I have 100 samples and I got some 100 types of speeds of different vehicles. Now if I have to calculate the time mean speed, it's simply an average. It's an average of all the samples. So that is, you add your speeds and you divide it by 100, so you get an average speed. So it's a spot speed as well as we can consider it's a time mean speed. So for a corridor, so because it's a corridor, it's not a point based thing, so how do you measure this spot speed? So you have to conduct spot speed at each locations maybe, which may not be feasible at all times, right? So we can say that this corridor level or system level things, or even you can imagine it's not a corridor, it may be a network. So it's a typical network, urban network. So then it will be more challenging to conduct a spot speed study. So in such cases, should we go for then space mean speed? So space means we are taking this space and we are, by the use of suppose installing video cameras, we are seeing this portion of the road, suppose 100 meters of the road, and now we are using harmonic mean speed formula, which I think you have already read in module 2 mostly, in microscopic and microscopic parameters and how those are done. So then you calculate the harmonic mean, which is called the space mean speed. So even that is also challenging for a this kind of corridor level measures, right? So in that case we go for actually average vehicle speed. So here average vehicle speed means whatever the vehicles are contained in that network or that corridor, we will take the average of this all vehicles. It's a network wide performance measure, this average vehicle speed. Maybe we can also say in a more correct way that network average vehicle speed. That will be, I think, more appropriate term for use. So then we know that your 3 is your A. So now in case of linked based measurement, because it's a small link of 100 meters, 500 meters, so always we can use this space mean speed, right? So link based is space means, and the point based is always spot speed. So this is your correct answer. 3A, 2B and 1 is C. So then the sixth one is, which of the following statements are true with respect to a calibration of a micro simulation model? Okay. So what is a calibration? I already discussed that. Suppose you want to replicate the field scenario. Suppose you want to match the field measured flow with our model, traffic model flow. So how do you do that calibration? So here some statements are given. So you have to say that which are the correct statements. So the first is default micro simulation parameters are modified. Obviously this is true because I already talked to you about that carpooling model parameters. So suppose they have said that for lane changing mode we will take this kind of parameters, to 0 to 100 we will take 50, but that 50 is may not be representing the correct scenario in our case. So we have to modify, obviously we have to modify the parameters. That is always true. Then the calibration steps is performed after the validation steps. Okay, so I missed that validation step, so let me discuss it here. So suppose let's imagine you have a this kind of traffic corridor of suppose 5 kilometers, and you already collected data and developed model and you calibrated and you found that these are my optimal parameters of carpooling, right? So some parameters are there, that how those interact, how vehicles will interact, about those parameters. So these are some size 1 2 3 4 5, these are parameters. So now it is it is necessary to do a validation. So suppose for a particular traffic condition during peak hour, you and particular road geometry, you have done this calibration, but how to ensure that these calibration parameters are also valid for off-peak scenarios? It may not be valid. Even if you want to, because in off-peak the traffic volumes are less than peak, but in those off-peak also you want to calibrate the model. You do not want your simulation to go haywire, right? Another point is, suppose for this road geometry your parameters are sufficient. Suppose you have some 2-3 stretches in a same city maybe, so you want to achieve a global calibration kind of thing. That same parameters I will use for my different models. So in this case, due to variability in your traffic as well as your road geometry conditions, number of lanes, then the width of the lanes, those things, and the parking and encroachment, those scenarios are different. So is it that your same parameters are valid for this also? It may not be so, right? So in that case also you need a validation. Validation means you take new parameters and you perform that calibration once again and see that using that same parameters, am I is it possible that I am achieving target traffic flow? So that has to be ensured. So another validation point is, suppose you are calibrating for a particular one scenario, suppose traffic flow, so you match the traffic flow. So what about the speed? Are they matching the actual operating speed on field and in your model? So is it that your time headway distributions are matching? Is it that your acceleration distributions are matching? Is it that your some other parameters which is relevant to your study? Suppose you want to use this simulation model to do a safety analysis. So suppose for that safety analysis, what could be your measure of effectiveness? So is it that for the safety analysis also your field observed safety values and your this values, those are matching or not? So this has to be ensured through a validation steps. So until and unless you perform a validation, we cannot be sure of your or cannot trust your simulation model. So this is also a very important step of a simulation model. So obviously it is performed after the no, this is wrong, because it has to be performed after the validation is performed after the calibration, not the other way around, right? Here it is written the calibration step is performed after the validation. So then the last is statistical tests are used to compare the similarity of estimated results and the empirical data model parameters. Okay, statistical test we can use it. Suppose I got a distribution of traffic flow like this. Suppose it's a normal distribution and it's a from field I got this. Now I develop a model and I found maybe this sort of distributions. So which is a shifted kind of normal distribution. So if I use any statistical test like chi-square test or case two sample test, I can actually say that whether these two samples are statistically same or they are different. Because if they are different, then that means that my model is not able to replicate my field conditions, right? Because the distributions are different. Because although generally we use average value to replicate anything, but if you see, because there are large number of samples you can generate from your model as well as from your field sample data, if you can generate a distributions using sufficient sample size, this will be a better indicator, right? So actually it is also true. So then the next one is, which of the following statements are true with respect to Weiderman car following model? Okay, faster vehicle approaching a leader will decelerate if SDB threshold is crossed. Okay, faster vehicle approaching a leader will decelerate if your SDB threshold is crossed. If relative distance between leader and the following vehicles is more than SDX, then the driver follows the leader without consciously decelerating and accelerating. Okay, this question I have to also check the answer because I do not remember the formulation of this Weiderman car following model exactly. So maybe I will check. I have the solutions also with me. With respect to car following model, let me check whether I am having this or not. So okay, so which of this question, and let me zoom it so that you will be able to also see. So which of the following parameters are true with the statements? So here seeing if your faster vehicle approaching a leader vehicle, so the following vehicle is faster, is approaching leader vehicle, will decelerate if your threshold is crossed. Okay, so it is true, because if your del x means your distance is greater than your SDX, not SDV, then there is no influence on the following vehicles and the driver seeks to reach the maintenance desired. If distance to the falls below the desired size, then the safe distance is the will decelerate. So if your relative distance between the leader is more than SDX, more than your safe distance, SDX means, then the driver vehicle without it will not react. If your faster vehicle will accelerate if your distance is crossed. Okay, if it is less than that distance, then will be crossed. This is distance and this is okay. Maybe for better understanding, we should actually read the main material itself. Traffic engineering week 9, resume week 9. So this is regarding so here if you see free flow state, this is your reaction time, perception threshold is, this is SDX and this is BX. BX means for deceleration and SDX is for acceleration. So desired space between the front side of two successive vehicles, desired minimum, okay, BX is the desired minimum following distance. So if it is less than that, then only it will react, otherwise it won't react. So that makes sense. And action point, a driver is consciously observed that he is approaching a slower leading vehicles. So if your SDF is crossed, then only, so it is crossed and it is lesser, because so it is crossed and it is lesser. So is it so? SDF threshold is crossed means you are already you are seeing that it's a slower vehicle and you have to maintain this distance. So if it is crossed, because your faster vehicle is traveling at the slower vehicle, so it's a true statement, and your BX is the minimum threshold. So your that threshold, if it is breached, that only it will accelerate, because it's a deceleration threshold. Okay, so due to this is already written that if your distance to the preceding vehicles falls below to the desired safety distance, then obviously you will be accelerating, not decelerating, right? Because your BX threshold is crossed. So this is the final one from my side. Now if you have any query, you can ask. You can ask if you have anything. Yeah, if you are speaking, that you have to unmute your microphone. I don't know whether you are speaking or not, but if you are speaking, that you need to unmute, because you are muted. Okay, so even if it is not included here, you can ask any question if you have anything from this module, this scaffolding. Okay. So also, did you understand the last one? I hope it is also clear. Okay. Okay, if it is so, then I think this is from my side for today. Maybe we will meet in the next week. That is, the date will be on 31st March with the content of traffic management, I think, and some parking. Parking is not included. I think traffic management measures are included. So thank you for joining in today. Okay, thank you. So I will be closing the session.